Hi all, in this video I'll be explaining the tutorial questions I gave you in class. So the first question is question number 2 and I'll be discussing until question number 6 in this video. Alright, let's get started. So the first question is question number 2, whereby calculate the energy of an electron at its excited state before it drops to produce the second line in Lyman series. So this question, you have to first understand that the energy that they are asking to calculate is the energy of an electron at, maksudnya elektron tu belum jatuh lah, right? Dia duduk dekat excited state. So what is that excited state? Where is that excited state? We have to continue reading to the next information, whereby you have to find the excited state that produces the second line in Lyman series. So Lyman series N final would be 1. So the first transition would be right above it, whereby it drops from N2 to N1, and the second transition would be an electron falling down from N3 to N1. So there we know that the excited state is N equals to 3, and since we are calculating energy of an electron at its excited state, we have to use this equation, substitute correctly, and the final answer over here, you can give it in 2 decimal place. Okay, so for this question, please maintain the negative sign, because this negative sign means that the electron is in the nucleus. Sorry, in the nucleus pula, in the atom. Alright, for transitions, then we have to do a conclusion. We can see the next example, but for this case, where the energy of the electron at a specific energy level, we just leave the answer in negative. Alright, next question, question number 4. Calculate the wavelength and energy change for a spectral line produced when electron falls from N5 to N3. So here the question is very clear that N5 is going to be our N initial, N3 is going to be our N final. And we have to calculate the wavelength and energy. We have done questions like this in class. So first, since they're asking wavelength, you start calculating the wavelength. Alright, so wavelength, we have to use the formula which says N1 and N2, whereby N1 is smaller than N2. Since we have two numbers over here, 3 and 5, it is clear 3 is the smaller number, N1, and 5 is the larger number. Okay, so here wavelength is to be 1.28 times 10 to the power negative 6 meter. Now, a quick word remember, I would say lambda equals to wavelength. If you see 1 over lambda, it means wave number. So this is a quick check for me in class coming Monday. If you have watched the video, if you watch the video, I will test you on this because I did not tell you this in class. So please remember this. 1 over lambda means it is wave number. Alright, let's continue. So next, since we have found the wavelength, we can find the energy using our SPM formula, which is delta E equals to Hc lambda. When you use this formula, automatically your final answer will be in positive answer. Okay, so you don't have to give a conclusion that energy is emitted. But let's say if you are using the Rydberg formula, whereby N initial squared minus N final squared, you would end up getting a negative answer. So this negative here for transition simply means that, therefore, energy released or energy emitted equals to 1.55 times 10 to the power of negative 19 joule. Okay. All right. So since we are falling down to n equals to 3, what would be the series and what is the electromagnetic, the region of electromagnetic spectrum? That would be Paschen series and it would be infrared. Okay, right, let's go on to question number 5. So question number 5 here is they have given you the wavelength in nanometer was observed in Balmer series aligned with wavelength for its 6.4. It was observed in Balmer series. Calculate its frequency. Okay, if you can see by now, we just have to know the concept very well. Question can be asked in any direction. Okay, so you must be prepared. Right. So for the first question, I think you can use back your SPM formula over here, whereby frequency equals to speed of light over lambda. So speed of light over lambda. Now here's the catch. Lambda, the wavelength, was given to you in nanometers. You have to convert it into meter. So from meter, you want to convert to nanometer, you just times by 10 to the power of 9. Okay, but from nanometer, you want to convert to meter, you have to times by 10 to the power of negative 9. So please remember that. Next would be, the final answer would be this. I think you can have a look. And the unit for frequency, try to maintain it as negative 1. Next would be finding the initial and final values of energy levels associated with this emission. Since it is Balmer series, we can clearly know that n final equals to 2. So what would be N1? What data can we use? We can use the wavelength data in this case and insert it in this formula. So now we are working backwards, whereby we know the smaller number is definitely going to be 2 because it's falling down to 2. Therefore, what would be the initial energy level? If you do the calculation correctly, make sure to do it step by step, we would get N2 to be 4. But please don't leave your answer here. Common student mistake is they just leave the answer here. The question wants you to identify the transition of electron. So you have to mention at the end that the electron is making a transition from N4 to N2. Okay, because the initial energy level is 4 and the final energy level will be 2. All right, I hope that is clear. And the next thing that I want to highlight in this question is, please be very, very careful on using the correct Rydberg constant. That would be, for calculating wavelength, you must use 1.097 times 10 to the power of 7. Okay, 10 to the power of 7 per meter. All right, let's get going to the next. And they wanted region. Okay, so it's good to remember region. It will give you 1 mark in exam. So region for Balmer series would be visible light region. All right, okay, the final question for this video is converting an emission spectrum, an emission line spectrum, into an energy level diagram. We have done this practice in class. So a quick recap, this would be our first line, this would be our second line, third line, and fourth line. So since this is the Lyman series, all transitions will end up in n final equals to 1. So what would be the first transition in the Lyman series? It will be just one place above, so N2 to N1. This would be N3 to N1, and this would be N4 to N1, and this would be N5 to N1. So once we have identified that, I think we can safely draw our energy level diagram. And this is our energy level diagram. There is a mistake over here. Y-axis should be potential energy. And n equals to infinity must be colored, I would say. Okay, try to make it look like a thick band. Right. And now we are going to label line P, Q, and R as shown. This is quite clear. All right, so that's the answer for 6A. And for 6B, we have to calculate energy corresponding to line Q. So line Q starts from N5, falling down to N1. Using the energy formula, the Rydberg change in energy formula, using the Rydberg equation, it is clear. Sorry, what was line Q? Line Q, was it 5 to 1 or 4 to 1? Let me just have a look. Line Q is 4 to 1. Okay, so there is a mistake in this. 1 minute, there is a mistake here. So line R, let me check. Line R is 3 to 1. Okay, again. Now I know. Let me just quickly change the labeling. The labeling has run a bit. Oops. Okay, let me just cancel it. 1 minute and cut it and write it better. That works. Okay, I think okay, this would be N3, this would be N4, this would be N5, and this would be N6. Okay, much clearer now. All right. Now, where was I? Okay, so transition for line Q would be from N4 to N1. Final answer, you have it in negative sign. So please do a conclusion. Energy emitted equals to 2.04 times 10 to the power of negative 18 joule. All right, or energy released. That'd be good. Okay, so that's all for this video. I'll do another video for the remaining questions. Thank you.